The previous class, madam has already discussed regarding the sensors and actuator. So I hope all of you understood the clearly the definition of sensors and actuators and where exactly we are going to use them in different embedded applications. So madam has already covered a few of the sensors and actuators such as LEDs, segment display, right? And a few more. Now today I will be starting with a few more components. Right, so these are the few things which I'm going to discuss in today's class. That is with respect to piezo buzzer, push button switch, and I will start with the communication interface. In that I will try to cover I2C, which is one of the most important on-chip communication interface used with most of the embedded systems. Now coming to the piezo buzzer, as shown in this particular figure, most of you have seen, I think, whoever has done few small or mini projects with the help of Arduino, you might have seen this kind of a buzzer, right? Now piezo buzzer is a piezoelectric device for generating audio indicators in the embedded application. Piezoelectric buzzer contains a piezoelectric diaphragm which produces audible sounds in response to the voltage applied to it. The piezoelectric buzzer are available in two types: self-driving and external driving. The self-driving circuit contains all the necessary components to generate sound at a predefined tone. The self-driving circuit contains, right, as I told, all necessary components to generate the sound at predefined tone. It will generate a tone on applying the voltage. External driving piezo buzzers support the generation of different tones. The tone can be changed by applying a variable pulse train on the piezoelectric buzzer. A piezo buzzer can be directly interfaced to the port pin of a processor or a controller. Depending on the driving current requirements, the piezo buzzer can also be interfaced using a transistor based driver circuit, as in the case of a relay, which you have seen in the previous class. Now coming to the push button switch. Now as shown in this figure, you people have also seen this push button if you've done some small projects with Arduino. It is an input device. Push button switch comes in two configurations, namely push to make and push to break. Now we'll see what is push to make and what is push to break. Push to make configuration, the switch is normally in the open state and it makes a circuit contact when it is pushed or pressed. Okay, the normal switch. Now in the push to break configuration, the switch is normally in the closed state and it breaks the circuit contact when it is pushed or pressed. It is exactly reverse compared to the normal push button switch. The push button stays in the closed or push to make type or open push to break type state as long as it is kept in the pushed state, and it breaks or makes a circuit connection when it is released. Now as shown in this figure, there are two configurations: low pulse generator and high pulse generator. Now depending upon the port pin connection, whether it is before the switch or after the switch, we can have these two configurations. The push button is used for generating a momentary pulse. In embedded applications, push button is generally used as a reset and start switch and a pulse generator. The push button is normally connected to the port pin of a processor or a controller. Now depending on the way in which the push button, as shown in these two figures, interface to the interface to the controller, it can generate either a high pulse or a low pulse. Now next, coming to the communication interface, very important part of the whole embedded system design. Most of the industry are working with respect to communication interface. Now most of the fresh engineers who enter into embedded application development jobs, they will be given with the data sheets to understand this communication interface hardwares. Then they will be asked to program part by part. So communication interface is essential for communicating with various subsystems of the embedded system and with the external world. The communication interface can be viewed in two different perspectives, that is onboard communication and external communication interface. So onboard communication interface is nothing but device or board level communication interface such as serial interface like I2C or I2C, serial peripheral interface SPI, universal asynchronous receiver and transmitter UART, one wire and parallel bus interface. Now these all are examples for onboard communication interfaces. Now coming to the external communication interfaces, we have product level communication interfaces such as wireless interfaces like infrared, IR, Bluetooth, wireless LAN, Wi-Fi, radio frequency waves, RF. Then we have GPRS and wire interfaces like RS-232C, RS-422, RS-485, and so many variants are there. And we do have the USB, Ethernet IEEE 1394 port, parallel port, CF2 interface, SDIO, PCMCIA, etc. Now the internal integrated circuit, or also pronounced as I2C, is a synchronous bidirectional half duplex two wire serial interface bus. Alright. Onboard communication interface refers to different communication, as I told. Half duplex means one directional communication at a given point of time. The concept of I2C bus was developed by Philips Semiconductors in the early 1980s. Now it is called as NXP Semiconductor. You can Google down and you can check out in the Wikipedia how exactly the Philips has started his journey. Previously it used to be called as Philips Semiconductors or Electronics, and slowly they removed that electronics part, and mainly recently from 2013 onwards they are mainly concentrating on the development of healthcare products. Actually, the Philips started with the production of light bulbs. Then slowly they shifted from so many other variants of embedded system developments. Right, the I2C bus was actually developed by Philips in the year 1980s. The original intention of I2C was to provide an easy way of connection between a processor or controller system and a peripheral chip on television sets. So previously you might have heard, I don't know how many of you have seen, there were Philips TVs, the big TVs were there with the dome shaped TVs from Philips, very famous. So I2C bus was developed by Philips just to make the interconnection between the processor and different peripherals which were used for the production of TVs. The I2C bus was comprises of two bus lines. One is serial clock, SCL in short form, responsible for generating synchronization clock pulses, and serial data, SDA, responsible for transmitting the serial data across the device. I2C bus is a shared bus system to which many number of I2C devices can be connected. Devices connected to I2C bus can act as either master or slave. The master device is responsible for controlling the communication by either initiating or terminating data transfer, sending data, and generating necessary synchronization clock pulses. Whereas slave devices wait for commands from the master and respond upon receiving the commands. Master and slave devices can act as either transmitter or receiver, both. Regardless whether a master is acting as a transmitter or a receiver, it is a duty of the master that synchronization clock signal should be generated by itself. I2C supports multi-master on the same bus. The following bus interface diagram illustrates the connection of the master and slave devices on the I2C bus. Now, as shown in the figure, we have a master, right, and there are two slaves. For example, we have considered E square prom as the first slave and one more device as the second slave. Right, now master has to generate the synchronous clock signal right? Now these are the buses. You can see the clock and the address bus, the data bus, clock and the data bus has been connected to the centralized I2C bus to the master. Master is going to generate the signal, that is clock synchronization. Then depending upon whether it is a read and write, the communication will happen with respect to a particular device depending upon the address for which it has generated. For example, this master processor has generated a signal for slave 1. Then depending upon the address generated, the signals will reach to slave 1. If it is for slave 2, once again the address will change and the master will send the signals to slave 2. Right, this is how the I2C is going to operate. I will be explaining in detail how this communication happens with respect to the signals, the two important signals, that is SCL and SDA. SCL is for clock synchronization and SDA is for data transmission. The I2C bus interface is built around an input buffer and an open drain or collector transistor. When the bus is in the idle state, the open drain or collector transistor will be in the floating state and the output lines SDA and SCL switch to the high impedance state. For proper operation of the bus, both the bus lines should be pulled to the supply voltage, that is plus 5 volt if we are using TTL family, or plus 3.3 volt if we are using CMOS family. Now most of the I2C buses are coming with a CMOS, so that's why the voltage will be 3.3 volts using a pull-up resistor. The typical values of resistor used in pull-up are around 2.2 kilo ohms. With pull-up resistors, the output lines of the bus in the ideal state will be high. The address of the I2C device is assigned by hardwiring the address lines of the device to the desired logic level, done at the time of designing the embedded hardware. Now, the sequence of operations for communicating with I2C slave device is as listed below. The master device pulls the clock line, that's the first step, the burst to high. Then the second step, the master device pulls the data line SDA to low. So what are the first two steps? Master device pulls the clock signal or the clock line SCL to high and SDA to low. This indicates the start condition for data transfer. Now the third step, the master device sends the address. It can be 8 bits or 10 bits depending upon your applications. The slave device to which it wants to communicate over the SDA line, that is data line. Clock pulses are generated at the SCL line for synchronizing the bit reception by the slave device. The MSB of the data is always transmitted first. This is the protocol which we have to maintain in I2C. First, the MSB data bit has to be transmitted. The data in the bus is valid during the high period of the clock signal, only during the high period of the clock. Next, the first step, the master device sends the read or write. If bit value is 1, then it is read. If bit value is 0, then it is write according to the requirement. The master device waits for acknowledgement bit from the slave device whose address is sent on the bus along with the read and write operations. Then the slave device connected to the bus compares the address. The slave device with the address requested by the master device responds by sending an acknowledgement bit, that is bit value 1, over the data line. Upon receiving the acknowledged bit, the master device sends the 8-bit data to the slave device over SDA line. If the requested operation is a write to the device. If the requested operation is read from the device, the slave device sends the data to the master over the SDA line. The master device waits for the acknowledgement bit from the device upon byte transfer complete for a write operation and sends an acknowledgement bit to the slave device for a read operation. So here first the initiation will happen with respect to the address. The synchronization clock signal has to be generated. Data has to be sent to the address device. Now there are two possibilities. The either master can write onto the slave or it can read from the slave. If it is write from master to the slave, then it has to wait for acknowledgement signal from the slave. whether it has completed reading the content or no. If it is a read from master from the slave, then it has to send acknowledgement signal to the slave telling that I have finished my read operation. The master device terminates the transfer by pulling the SDA line high and the clock line SCL is at logic high, indicating stop condition. So this is how I2C bus or protocol in general it works. I2C bus supports three different data rates: standard rate 100 kbps, fast mode 400 kbps, and high speed mode around 3.4 mbps from kbps to mbps. Now these I2C bus find application in most of the embedded applications. We can also check its working with the help of a simple Arduino project also. If you are interested, you can take that I2C IC. Some of the Arduinos will come with the on-chip I2C bus, and you can connect external devices and you can see how exactly to program this. You will get online code for programming I2C bus. If you're really interested, please try to do this. Right now, that's all for today's class. We'll see the remaining part of the communication interfaces in the next class.